So let's continue with chapter 11, where we're learning about the forces that objects feel when they're in magnetic fields. Just to remind you, the things that we were aiming to learn about in this chapter are, we learned really a little bit about magnets and how they interact. Remember, opposite poles attract, like poles repel, blah, blah, blah. We're looking at two different things about things that feel forces when they're in a magnetic field. In the previous lecture, we looked at moving charges. And now in this lecture, we're going to look at when you put something, a current-carrying conductor, so a wire that has current in it. If you put it in a magnetic field, it will feel a force. And another thing that's going to be covered in a separate video, it's actually a video I already had done, and that's about if you have a loop of current, how it's going to behave in a magnetic field. So let's really quick review what we talked about in the last lecture. So basically some of the things that we learned was that magnetic field lines are not lines of force. And you might be like, well, what does that mean? Because it's not obvious. Well, part of the reason that we say that is because when an object in a magnetic field feels a force, it turns out that force is not in the direction of the magnetic field. And that's different from what we found with electric fields. If you remember, the expression for the force of a charge in an electric field is just F equals QE. And so these two are either parallel or anti-parallel. And so that's why for electric field lines, we can say that they're lines of electric force because the force and the electric field lines are in the same direction. Okay, not true for magnetic fields. In fact, we have to get into this right-hand rule because the way that we express the force on a charge moving in a magnetic field is that it's the charge times the velocity, which is a vector, crossed with the magnetic field, which is a vector. And so here you see that this is not parallel, that's the force vector, to the magnetic field. In fact, it's perpendicular to it. The other thing, when we use the right-hand rule, we're finding a vector. Force is a vector. Sometimes we also want to know, like, how big is that vector? And so the magnitude of the force is given by this expression, where theta is the angle between the velocity vector and the magnetic field vector. And so from that, we found out that the largest force is experienced if the charge moves perpendicularly to the magnetic field, and it experiences zero force if it moves parallel or anti-parallel to the magnetic field. Again, these are all reviews, and so I'm going through them pretty quickly. If you're having trouble with it, hopefully reviewing the previous video will be helpful, or you ask when we all meet together in class for questions and problems. The other thing that we have to get used to, and we're going to be using it pretty frequently, is the right-hand rule. Because finding the direction of a cross product, so this is what we call a cross product. It's also called a vector product. I don't really like that name as much, so I never use it. When we take two vectors, it's one of the mathematical operations we can do with two vectors is taking their cross product. The answer is a vector, which is why it's also called the vector product. The vectors have direction, and the way that we figure out the direction of the cross product is through the right-hand rule. So all your righties, put your pencil down before you try it, because it doesn't work with your left hand. And you first lay your hand along the direction of the first vector, which in this case is always the velocity. And then you curl your fingers towards the second vector, which is the magnetic field. Your fingers can only curl one way, because your knuckles only bend one way. And so when you have your hand oriented in the way that will allow you to curl your fingers from the first vector to the second, your thumb will give you the direction of the V cross B. And so in this picture, they're illustrating that. And the last thing that we went over in the previous slide had to do with what happens if a charged particle moves into a magnetic field where it's moving strictly perpendicular to the field. Remember that here the crosses mean that the magnetic field is into the page. We see that the charged particle is initially moving to the right down here. And so the way that we can sort of explain the behavior of this charged particle is we start with F equals ma, and because the velocity and the magnetic field are perpendicular to each other, that means the sine of 90 is just 1. So the force is just QVB, and we find that this force ends up acting as a centripetal force, and so we can write the acceleration as centripetal acceleration, v squared over r. And, you know, there's different things that we want to find about the motion of this particle moving in a circle. Basically, it ends up going in a circle. You know, we can find the radius of the circle, we can find the angular velocity, etc. And basically, what I'm advocating is remember this and rearrange it to find the next quantity that you want to know. Don't memorize all those expressions. Total waste of your brain power. Okay, so that finishes everything new. Now we're going to get into something, that finishes everything old. Now we're going to get into something new. There's two things going on here that we're going to talk about. The first is to just realize that it turns out that a current creates a magnetic field. And that's what this picture is trying to illustrate. Notice we have a compass and a wire. And initially, the compass is just pointing north as we might expect. That's what compasses are for. But notice also that there is no current in that wire. But when we allow current to flow in the wire, notice that the compass is deflected. Also notice that if we change the direction of the current, the deflection of the needle in the compass changes. So what are we seeing is we're seeing that the current seems to cause a magnetic field. And not only seems to, but it does. So this is what the magnetic field looks like. Here we have a wire, the current's flowing straight up. In order to describe the magnetic field, we're going to use a right-hand rule again. This one's way easier to use. Just to kind of get to the end point, what we find is that when you have a wire that's carrying current, the magnetic field makes circles around the wire. Now, we still want to know the direction of the magnetic field, and so when you go in a circle, you can go two ways. You can go clockwise or counterclockwise, or you could just say, I go this way or that way. In order to figure out what way the magnetic field points in those circles that go around the wire, we use the right-hand rule. And the way you do this is you take your thumb, you point it in the direction of the current, and the way that your fingers curl when you curl them is the way the magnetic field curls around the wire. So the way that your fingers curl around your thumb is the way that the magnetic field is going to curl around the wire. So that means if I held my thumb and pointed it up like this magnetic field, my fingers, if I look at them over here, are going to be coming at me. And so over here, the magnetic field is coming out of the page. But if I then try to curl my fingers all the way around my thumb to get to the other side, they actually will point into the page, and that's what we see there. And this picture here representing the arrows on those magnetic field lines also mimic that. Sometimes we want to sort of take a cutaway view, so here again You might want to practice the right-hand rule and see if you agree with the direction of the magnetic field given by this current. But if we sort of imagine cutting those circles in half so that we're just looking at the magnetic field that's coming out at us and going in, above the wire, the magnetic field will be coming out of the plane, and below the wire, the magnetic field will go into the plane or into the paper. And so that's something you might want to practice to see if it makes sense to you. Remember, just put your thumb in the direction of the wire and then see which way your fingers point. So that's one thing that we are learning. The second thing, and really the last one, is it also turns out that if I put a wire that carries current in a magnetic field, it'll feel a force. Now, if you think about it, a moving charge in a magnetic field feels a force. And that force is given by Q, V, cross B. Well, current is just moving charge. So, current in a magnetic field should feel a force. All right, so let's imagine that the velocity here of the charge is perpendicular to the magnetic field, so that we can write the force due to one charge carrier would just be Q, V, D, B. Because remember, when we have a current, the speed of the charges is called the drift velocity, and that's why we're using V sub D. So that's the force on one charge. If we wanted to find the total force, we would take the total number of charges and multiply it by Q, V, D, B. All right? Now, how do we find N? So let's go to the next page. So we're saying that the force total is N, Q, V, D, B. The total number, well, so we have to decide how much of the wire we're going to take. So we're going to take a piece of the wire. Oh, actually. Forget that. It's a piece of the wire. It's the whole piece we're going to take. Sorry, didn't notice that. And in that wire, it has a charge carrier density. Remember that little n is the number of charge carriers per unit volume. And so if we multiply this by the volume of the wire, this will give us n. Well, the volume of the wire is the cross-sectional area times the length of the wire, which is given by this. And here's the cross-sectional area. So F total can be written as little n A L Q V D B. So it was a lot, but if you remember from a previous chapter, we found an expression for the current in a piece of wire could be expressed using these terms: density of charge carriers, charge per unit carrier, drift velocity, cross-sectional area. So we can replace all those terms that we see up above by just A. The force total will end up to be I, L, B. Okay, so now we see that we've sort of changed from looking at an individual charge carrier to a piece of wire with a current flowing in it, and it's in a magnetic field. And so this is kind of here, just kind of writing it out. If you want to look at that later, it's really all the things that I already went through. Now, the next thing is we know the magnitude of the force when, the current was perpendicular to the magnetic field was ILB. If it's at an angle, we're going to find it's ILB times the sine of theta. So it actually will end up mattering what the angle is between the current carrying wire and the magnetic field. And that ends up saying, well, that looks like you could also express this using the right-hand rule or a vector product, which is also the cross product. And the way that we write it is IL cross B. Now this might be kind of weird. You might have expected that when because I know that force is a vector and I'm going to write it as a cross product, I need to take the cross of two vectors. And you might have expected that the current would be the vector because it definitely has a direction in the way it flows. But if you think about it, up until now, when we dealt with current, we treated it like a scalar, and we're not going to change in the middle of the game. So current still has to be a scalar, and so what we do is we take the length of the current carrying wire that we're talking about, and we make that length the vector, because that can be a vector. We've used, displacement's a vector, it's a length. And the direction of the length is always going to be the same direction as the current flow. So the way we express the force on a current carrying wire is IL cross B, where this is the length. And that is really all that we're going to do for this part. I've posted a separate video about finding the force on a loop. Put a current loop in a magnetic field. It'll be better to separate it, and like I said, I already had that video done. So enjoy.